So what shape is this? It's a kite, right? And sometimes it'll tell you, sometimes you just have to be able to recognize it from the drawing. Is it a kite if the diagonals are not drawn in? And yeah. So if it's like that, is that still a kite? Yeah. So sometimes you'll be given a figure without those things in the middle, and it looks a little strange, but we just have to know that it's still a kite. And honestly, as we get through this unit, it might look a little bit like a rhombus, so we'll have to be careful that we distinguish between which is which. Quick review of our kite properties. And for that, that's not it. There's what we wrote from Friday. No, this was Wednesday for you guys. So remember, we've moved into the section. The rest of our course will just be on quadrilaterals, with the exception of a few problems. So the first one was a kite. We found there were 4 properties plus a definition. And most of those properties came from the fact that this is 2 congruent triangles. So the definition is a quadrilateral with 2 pairs of congruent consecutive sides. So going around the figure as you go across 2 sides in a row are congruent. And then opposite sides are not congruent. So if you want to add that to your sheet, just as a clarification, opposite sides not congruent. Anybody else need to come up to get a sheet that was gone? And, right. So that was our definition. But then we note that we have perpendicular diagonals, which creates 90-degree angles, which creates right triangles, and that means we use Pythagorean theorem quite a bit with kites. Okay, number 2, long diagonal bisects the short one. And usually you can tell which is which. But the other way around is not true. So the short does not bisect the long diagonal. And then the long diagonal bisects the angles on it. So that was these 2 pairs on the ends of the long diagonal. And then finally, the 2 angles on the short diagonal are congruent. So that was this way. Sorry. Now keep in mind that kites can be oriented in any way. That's not always going to be facing straight up like this. So your first job would kind of be to identify which is the long, which is the short diagonal. And we define diagonal up here, a line through the quadrilateral that connects the opposite vertices. And that's going to be true of all these quadrilaterals. They will all have a diagonal. Okay, so with that, hopefully we can answer this question. So OQ is 33. Of course, labeling your picture is hugely helpful. RS is 65. OR is 7x, excuse me. Okay, and currently those look to be completely unrelated. So we need to use some properties to move stuff around, copy, paste, so that they're at least together in one triangle. Again, with kites, you're thinking triangles a lot. So what would you copy paste? I can think of 2 options. Okay. So he's noting that RP is the long diagonal. And so it's bisecting this short diagonal. And therefore, these 2 pieces are congruent. So let's copy our 33. And then from there, we're going to zoom in on just this triangle to solve. What kind of triangle is that? Yeah, that's a right triangle. So we have used 2 properties from our list. Number 1, that the long diagonal bisects the short one. So we were able to copy the 33. And then number 2, the 2 diagonals are perpendicular. So we can create a right triangle in there. I said there were two options. The other one would be to copy and paste 65 to the other diagonal or the other side length, so RQ. And either way, you'll end up with the right triangle. Okay, from there, how do we solve? We have lengths in a right triangle. What's our tool? Good. Yep, a squared plus b squared equals c squared. C always has to be the long side, which is always across from the 90. And so these other two look like this, 7x whole thing squared. Make sure you put that in parentheses so we don't only square the x. And then 33 squared equals 65 squared. And these are kind of big numbers. 7 squared is 49, and then we get x squared. 33, I don't know those. 33 squared, 65 squared. So 1,089 and 4225. Now here's the good thing. Even though we have a squared term, we don't have to factor because we don't have an x. We just have x squared. So that's going to be super nice. Okay, let's get our like terms together. And oh, come on. $31, $36. Divide by 49. How are we going to get this x squared by itself? How do you undo x squared? Square root, yeah. Okay, so I will show that here in just a second. So, divided by 49. Oh, 64. So square rooting that is easy enough. What's the square root of 64? 8. So x is 8 in that case. All right. How'd you do? Raise your hand if you got that one. If you got all the way to x is 8. Going around on the homework, quite a few of you didn't finish, and you definitely want to, so you have the practice. If you didn't get to it, please do it. I've kind of communicated this unit will have a ton of properties that you have to know, and the only way to really get familiar with them is to practice it. So please do that homework. On Friday, we're going to have a quiz over polygon angles, so interior and exterior angle sums, and then trapezoids and kites. So we'll talk trapezoids part of today and tomorrow. Then we'll review, and then quiz on Friday. And you got to know your properties. There's a lot there, so make sure that you're doing your homework. Speaking of that, let's go check. So pull that out. If you didn't do it, don't just copy answers. It's not going to help you. This is for those of you who did. So 18 diagonals of a quadrilateral form 2 acute and 2 obtuse angles. The diagonals do. Is this a kite? No, because they should be perpendicular. Okay. 19, the diagonals of a quadrilateral form right angles and its side lengths are 4, 4, 6, 6. Could this be a kite? Sure. If those congruent sides are consecutive, not across from each other, then yeah. Number 20, 105.5 for both those angles. Those are the congruent ones. And for that, we just took the interior angle sum and divided it by 2 to split it. Okay, 21, you should have got 25 and 90. Well, number 1 is 90 and 2 is 25. That was just subtracting from 180, so that was just triangle angles. 22, both are 118. Those are also congruent to each other, and we did it the same way as number 20. So interior angle sum of a quadrilateral divided by 2. Okay, 23, angle 1 is 90, Angle 2 and 3 are congruent, and they're both 63. So just to remind you that this is 90 here, and so we're told that this is 27, so it's like just adding those three up to 180. So 90 plus 27, and then subtract that from 180 for number 2. 24, both those angles are congruent, and they're both 107. 25, angle 2 is 51, and angle 3 is 39. How'd that section go, those of you who did this? Okay. Number 26, we have some x's now. For that one, x is 7, and I just added the 2x, 10x minus 6 up to 90. You could have also said that the 3, 2x, 10x minus 6 plus 90, those are all in a triangle, so they add up to 180. Number 27, you should have also got x equals 7. And again, it's the same idea. Angles adding up to 180. I'm only writing the 90 because if I add them up to 180 and subtract 90, then it's 90. Right? It's just saving a step. Okay, this one, we know we can copy y above the line because that's the long diagonal, and it bisects that angle. Note this one only shows one diagonal, and it looks a little weird, but it's okay. We know that those are congruent triangles as well. And with that, we can start by setting 5x minus 15 equal to 4x plus 13. That gives us x, and then once we copy, we have enough information to solve for y. Any questions on that one? That's a pretty good problem because there are two variables in one problem, and you have to solve for x first and then solve for y. And you get 28 for x, 32 for y. Okay, number 29. X is 4. Either way that you do this, so here's what I mean. In a kite, we know that 2 consecutive sides are congruent. So it's either GTGL or LO and TO. Either one of those pairs. But either way, you're going to solve to get x equals 4. And for that, since they're congruent, you just set equal. Number 30, so 6x plus 6 is pointing to an angle, and we know that angle is a 90. So set it equal to 90 and solve to get 14. A quick overview of this. This whole section was angles. And every one of them relied on either triangle angle sums or quadrilateral angles, which was 360. And then from there, those were all angles too. Now we were still relying on 180 degrees, but we were solving with x. And then finally, this one problem was a side length problem in this case. Questions on any of those? Okay. And then in terms of your other homework that I printed out for you, I want to work through these just as a reminder of how these can work for side lengths. So OY is 7, WZ is 4x plus 5, and OZ is 24. So this is very similar to the one we just did in the warm-up. Copy the 7, and now we have this nice right triangle right there. Guys, sometimes it's helpful. Actually, I want you to do this, to redraw that. Like that. And now we see it's in a right triangle. The thing to be careful with on this one is, well, you guys tell me. I'll write it, but I want you to tell me what to be careful with on this one. What have we seen so far? Is this is this going to be 16x squared plus 25? Not completely, right? There's a middle term, so that's only part of it. So we have to make sure that we expand this correctly. Meaning, write this twice and then distribute it out. Okay? And it's okay to do it in your head if you can, but definitely don't just square both terms. So we'll get 16x squared, and then we'll get 40x, because it's 20 plus 20, and then 25. How do we solve this kind? Yeah, how do you know that? Yeah, but the last one did too. Yeah. So you're both right. So we need to set this equal to 0 and factor, or try to. And the reason it's not like our starter, where we could just square root, is because of this x term. So that's what's telling us we have to factor, or at least try. Okay? And then, of course, with big numbers like this, I would look for a GCF. All right, so we get these add up to 625. Okay, a lot of you didn't do this one, so I'm going to leave it here. Let's get it ready to factor. Here's what you're looking at. I'm going to switch the order, or switch the side that it's on. But there's that. So I'm going to give you 2 minutes, maybe 3, to factor. Don't forget your GCF first, otherwise this one's really pretty tough. So see if you can solve that by factoring. How's this going? What's your GCF? Okay. Anybody figuring out the factors? This one's a little harder. Did you do it? Why? What are you thinking about? The factors? You don't have a calculator, huh? Are you gonna get one? Okay, it'd be helpful. You guys keep working. I'm just setting up things as kind of right behind you, just in case you're not there yet.
I got it right.
Factors of negative 150 that multiply or that add up to 5. That's what we're stuck on here. Can you think of them? We know they have to be 5 apart, so that eliminates quite a few. Like 30 and 5, that's not 5 apart, right? Or 50 and 3, those aren't 5 apart. How about these two? 10 and 15, how about that? Okay. The 10 is negative, so that it's negative 10 plus 15. That leaves us with the positive 5. Then we come in here and see if we can reduce these. Well, this right side cannot be reduced. It already is. But the left side needs to be first. So 2 goes into both of these. We get 1 and negative 5. And so that's x minus 5. Okay. And let's bring that over here. So we'll get x minus 5 times 2x plus 15 equals 0. All right, how do we solve from there? Two things being multiplied equals 0. That means one or both of them is 0. So we just check where that's true. So we set each piece equal to 0. Like that. And then you have these two little mini equations to solve that are usually pretty short. So like this one, we add 5, so we'll get x equals 5. How about the other one? How do we do it? So 2x equals negative 15. Divide by 2, we'll get x equals, you could say negative 7.5 or 15 halves is fine. All right, let's make sure that the negative version works. And what do you think? Negative 7.5. I'll just write it up here. If we put negative 7.5 in for that x, is that going to work in a geometry problem? How come? You're right, it doesn't, but why? Nathan, you were pretty sure. Yeah, it makes a negative side length. Can ZW be negative? No. Okay. So we call that extraneous, and we'll just go cross it off like that. So you do need to show that you found the answer, but show that it doesn't work. All right, and then lastly, if you did the other homework problem, this one's a lot easier. Here's the picture. It says VT, this whole length is 8, and then it tells us OV is this expression. And so we just set negative 2 minus 3x equal to half of 8, since it's just half that length. And we get x equals negative 2. And that time it works out. It's okay for x to be negative 2. All right, how about questions on kites? How are you doing on them? I know a lot of you still need to practice because you didn't do it. So finish those up. Please do it tonight. Here's what the very best student behavior would be to go home tonight and do those problems and then click on this video and look at the answers. You don't have to listen to me talk through them. Just check your answers at a minimum, okay? Or if you feel like that's too slow, come in like tomorrow at lunch and I can just show you the answers again. But you need some feedback to make sure that it went well. If you just do them to get them done, you're not getting the practice. All right, let's talk about trapezoids. So here's we'll put this in your notes, but grab the quadrilaterals reference sheet, get that out. That's where we're gonna write this stuff. So a trapezoid is a quadrilateral with exactly one pair of opposite sides that are parallel. That's its definition. Might as well just start writing it on there, I think. Guys, that word exactly is pretty important, actually. So make sure it stands out. So exactly one pair of opposite sides. Why is it like right on the edge over there? That says sides, it got cut off. That are parallel. So in your picture, the one that's provided, I would highlight that these two are parallel. And then it also shows you some vocabulary for naming those side lengths. So note that the bases, and it doesn't show up very good, so maybe make sure you can read base. The bases are the ones that are parallel. So base and base. And then the other two sides are called legs. Okay, there is another property that we need to add to this. And what do you think is true about those two angles I marked with green dots? Think back to your parallel line unit. Yeah, good. If we have parallel lines, we probably have some supplementary, maybe some congruent. In this case, we only have supplementary. So we call those same side base angles are supplementary. Actually, I'm just going to say they add to 180. Add to 180, which is supplementary. Okay, we have two pairs of those, so the green ones and the blue ones in my picture add up to 180. Do you think there's anything we can say about the diagonals? You don't need to draw these in, I'm just going to do it temporarily. Like, do these have anything special about them? Like the ones in the kite? Nope, not here. So not for just a regular run-of-the-mill trapezoid, we don't. Okay, just real quick. Note that even if the two parallel lines are vertical, we still call those bases. So the base word doesn't have anything to do with bottom or like sitting on the bottom or anything. So the two parallel sides are the base ones. Okay. All right, and then note that we have a special version of trapezoid called an isosceles trapezoid. What did isosceles do in a triangle when we added that word? Yeah, we had two congruent sides and two congruent angles. And guess what? It's the same thing here. So when it has the arrow down below for all of these on this paper, that means it has the properties of a trapezoid. So it has all properties of a trapezoid. Trapezoid plus we have some more. Okay? And here's what those are. Legs are congruent. And it's marked in the figure, but I feel like it kind of looks like it's just saying, hey, this is a leg. So maybe show that these two, like, make those congruent marks double instead, so it's obvious. So legs are congruent. Number 2, base angles are congruent. And this isn't marked in your picture, so make sure you show this. So those two angles are congruent, just like in a triangle, and so are these two angles. I'm just going to change the color of that real quick so it matches the picture. Okay, so now we have pairs of congruent angles. But also these two, so same side base angles, are still supplementary. So we have congruent, supplementary, congruent, supplementary. Lots going on, just because we added this word isosceles. Okay, number 3, the diagonals are also congruent. That's a little bit hard to show because they cross each other, but draw them in. Again, you'll have trapezoids that don't show this, but go ahead and draw them in and somehow just make note of your note down below that they're congruent. Guys, this allows us to do lots of solving, okay? So think about it. Do we have any 90 degrees in this one? No. So we're not going to be doing Pythagorean theorem stuff, but we could set like this diagonal equal to that diagonal and solve for x. We could set these two angles, or we could do like these two added up to 180 and solve for x. So there's lots of different versions. We've got to know, are we solving for side lengths or angles first? We'll come back to that probably. Okay, so here's an example. If angle R is 135, what are the other 3? Well, which direction should you go? Meaning you could go here or here, I guess, is how I would think of it. Yeah, I would go here first because what is true about angle Q and angle R? Yeah, those are congruent. So we might as well just copy and paste the 135. And then how do we go from R to S? Okay. And of course we know these two are congruent. So what is 180 minus 135? Good. And then we can copy over here. So that was one that didn't really involve x, but just angle relationships. Okay, a trapezoid sort of upside down looking. How do we get from 47 into the trapezoid? Go ahead, Elder. Linear pair. Yep, so 180 minus 147. By the way, how do we know this is an isosceles triangle? Yeah, like we have, it doesn't always say. Sometimes we have to read notation. Okay? All right, on your paper, the trapezoid paper, just do 1 through 7 tonight. That first section, it's all just about angles, kind of like we were just talking about. So 1 through 7. Don't assume every single one of those is isosceles. They are because they have notation, but don't just assume.